Yeah, we were in the middle of proving Greenfields' theorem about the equivalence of Poisson-Lie groups and Lie bialgebras, the categories of Poisson-Lie groups and Lie bialgebras, finite dimensional. And so we have done everything except, so we can, the most difficult part was to, for a given Lie bialgebra, to construct a Poisson-Lie structure on the corresponding group. And we did it, so we constructed the one co-cycle pi, but we still need to show that it satisfies the axiom of a Poisson bracket, that it defines a Lie bracket on functions. And recall that its Poisson bracket is defined by this formula here. So this axiom of Poisson-Lie group is this condition. This is equivalent to pi being one co-cycle. So and so so what, okay. And so we were checking Jacobi identity. So we computed the Schouten bracket of pi with itself, and we obtained that this is a certain one co-cycle psi. Well, I mean, if we use right translations, we can represent it by one co-cycle psi from G to wedge to 3 of the Lie algebra, and so we need to show that that psi equals to 0. So psi vanishes at the identity element, and so to show that it is identically 0, it suffices to show that it's a one co-cycle, and that is the following computation. So we need to show that this expression is 0. And so this, well, I mean, if we actually compute this first term, we will get 4 terms. We will get this thing, and we will also get these terms. And so we have to show that these cross terms vanish, the sum of the cross terms. So this is just a computation. So we compute in coordinates. So we have pi has components pi ij of x with respect to some coordinate system. And then the left-hand side of this expression is the following. So we have the sum overall indices pi ij of x pi rs of y times this thing here, which has various combinations of derivatives. And everything is alternated with respect to f, g, and h. So we have cyclic permutation, sum of a cyclic permutation. And then you get 4 terms, and you observe that the first term and the third term coincide after alternation, because they differ only by replacement of g by h. And also the second term and the fourth term also coincide after alternation up to sine, because they differ only by the replacement f by h, and also I by j and r by s. But this pi is skew-symmetric, so if we simultaneously replace I by j and r by s, it goes back to itself. And so that completes this proof of Greenfields' theorem. Any questions about it? No questions? Okay. So now So now we have shown that this pi exists, and so we proved Greenfields theorem. But the question is how to compute pi. So so to compute pi, we will write down the co-cycle condition pi of xy equals to pi of x plus adjoint of x times pi of y. But I'm going to substitute exponential of ta instead of y, and so then I get pi of x e to the ta equals to pi of x plus adjoint of x times pi of e to the ta. And so now I can differentiate this with respect to t when t equals 0. And on the left-hand side, then I get translation of pi of x by the vector field LA, which is the infinitesimal right translation by A on the Lie group, which is the same as the left invariant vector field corresponding to A. So I get LA times pi of x. But on the right-hand side, only the first term is independent of t, so it gets killed when I take the derivative. And the second term is pi of e to the ta conjugated by x. So when I differentiate this at t equals 0, as you know, we just get the co-bracket delta. So I get adjoint of x acting on delta of x. So this is a this is a system of differential equations satisfied by pi, and so pi can be found as a solution of these equations. So far it's easy to see that this equation has at most one solution with the initial condition pi of e equals 0, because we have these equations tell us how it varies in all directions. So in a sense, we have a connection. But we need to show that it's a flat connection. So we need to show that this system is consistent in order to show that the solution exists. Well, in fact, we have the following proposition, which tells us what the formula is for this pi. So it's explicit formula pi of e to the a. And of course, elements of the form e to the a are dense in our Lie group in analytic. So dense in the sense that, okay, they generate. In fact, such elements generate our group, and we know how pi changes when you take, and we know what is pi of the product xy. So it's enough to compute pi of e to the a. And the answer is the following, that it is e to the adjoint of a minus 1 divided by adjoint of a times delta of. Well, of course, we cannot divide by the adjoint of a, because that has zeros. But what it means is this power series. So if we formally write e to the x minus 1 over x and expand it, you get this power series, which is the same as the exponential power series, but with n factorial replaced by n plus 1 factorial. And so that's the answer. So we need to prove that this is the correct formula for the cycle pi corresponding to the co-product, co-bracket delta of A. And so, first we need to show that this differential equation actually has a solution. And then we will show that this solution must be of this form. So, so we need to check compatibility of the differential equations here corresponding to different elements A. So let's compute for this purpose so we have derivative along the vector field LA for every A, and compatibility means that if you compute derivative along LA and then LB minus derivative along LB and then LA, then it is the same as derivative along L of the commutator. And so let's compute that. So LA, LB pi of x. So we have LA times adjoint x delta of b. This is what LB pi of x is. And minus the same thing with b and a interchanged. Now, how do we compute this LA adjoint x delta of b? Well, we need to replace x by x times e to the ta and differentiate by t when t equals 0. So we've got adjoint x, adjoint e to the ta times delta of b. And we differentiate that by t at t equals to 0. Minus the same thing with b and a interchanged. And so when we do this differentiation, we differentiate, well, of course, we can interchange derivative with adjoint x. We obtain adjoint x acting on commutator of a with delta of b. Minus b and a interchanged. But then, well, we know that this expression minus the same thing with b and a interchanged is delta of a commutator b. This is the compatibility condition. So that means that we get exactly adjoint x acting on delta of ab. And by our differential equations, this is the same as L commutator AB of pi of x. So we've got that LA bracket LB acts the same way as L commutator AB. And that exactly means that these differential equations are compatible. So this means that solution exists by existence and uniqueness theorem of differential equations. And in particular, and it's unique if we have initial condition pi of e is 0. And now we can compute this solution. So we can actually look at just the one parameter subgroup, because we need to compute the solution at the point e to the a, which can just look at the one parameter subgroup e to the ta and solve the differential equation along this subgroup. So we will get d over dt pi of e to the ta. Well, according to the differential equation, this is just adjoint of e to the ta acting on delta of a. But pi of e to the ta, so our solution, putative solution that we wrote down, had the form of this here. And so if I replace a by ta, I have to, well, its nth term is homogeneous of degree n plus 1 because it has adjoint to the n and a. And so I have to multiply it by t to the n plus 1. And then when I differentiate that by t, acting by t to the n plus 1, I obtain n plus 1 times t to the n, and that cancels n plus 1 in the denominator, and then I obtain sum from n equals 0 to infinity t to the n adjoint a to the n divided by n factorial times delta of a, which is the same as e to the t adjoint of a times delta of a. And this is really the same as adjoint of the group element e to the ta acting on delta of a. So we get that this thing here is equal to this thing here. So we see that the putative solution that we have, at least it satisfies the differential equation along this one parameter subgroup and has the correct initial condition, because if we plug in a equals 0, we do get 0 here. All terms vanish except for n equals 0 term. In fact, sorry, in fact, all so in fact yeah yes, because if a equals 0, then delta of a is also 0. So so we have as y of e equals 0. So this is the same as right. Okay, so so since our solution exists and is unique, it has to be this along our one parameter subgroup, and therefore it has to be this everywhere. Okay, any questions up to this point? Questions? Okay. Yesterday there were many questions. Today there is no questions. Okay. Can everybody hear me well, actually? Okay.
Hi, can I actually ask a question? No, that's true. Couldn't you prove this formula by using what you did yesterday about integrating morphism of Lie group?
Yeah, that's right. Yes.
And then
you can derive. Yeah, you can derive this formula in that way as well. Yeah, that would be another way to get this formula. Other questions? Okay. So let me go ahead. So let me talk about the notion of dual Poisson-Lie group. So suppose we have, so the correspondence between Poisson-Lie groups and Lie bialgebras allows us to define the notion of dual Poisson-Lie group. So if you have a simply connected Poisson-Lie group, G, you can take its Lie algebra, and it's a Lie bialgebra, and then we can take the dual, so it's also going to be a Lie bialgebra as we discussed, and then we can use the correspondence the other direction and attach to it a Poisson-Lie group, which I call G star, simply connected Poisson-Lie group, with the Lie algebra of this G star is little g star. And so there is no, well, this is a procedure using this correspondence, but there is no simple geometric description of this dual group. And I also should say that sometimes a more natural group to take is not the simply connected group, but for example, algebraic group, like it is for semi-simple G, and then, you know, people just take non-simply connected one, but with the Lie algebra G star. So let me give some examples of duality of Lie bialgebras. Suppose G, so first of all, we discussed that there is a trivial example of a Poisson-Lie group, which is any Lie group with the zero Poisson bracket. So what would be the dual group for that? So let's take the Lie algebra. So Lie algebra is little g with a zero co-bracket. So then the dual Lie bialgebra is commutative. So its bracket is zero because it's dual to this co-bracket. But the co-bracket is the dual of the bracket of G. And so what we get is a abelian Lie algebra with a non-trivial co-bracket. And so the simply connected Lie group corresponding to abelian Lie algebra is just this Lie algebra itself with the operation of addition. And the Poisson bivector pi is constant in this case, and I'm sorry, not constant, but linear in this case. So it depends linearly on A, and it's equal to delta of A. So in particular, this shows that the theorem that to every Poisson, to every Lie bialgebra structure on G corresponds a Poisson-Lie structure on the group G, that requires the group to be simply connected. Because if you, of course, any discrete subgroup in our vector space G star gamma gives rise to a quotient group, G star over gamma. But in order for the Poisson structure to descend to that, we need this gamma to preserve this delta of A. And that's not automatic. Doesn't always hold. Now, the second example is the two-dimensional Lie bialgebras. So, for example, I will not check it explicitly, but it's an exercise. So the dual of B0 beta, which we defined yesterday. So this is the Lie algebra where x bracket y equals to y, and delta of x equal to 0, delta of y equals to beta x wedge y. So this is what this algebra is. Its dual is the same thing, but with parameter beta inverse, where beta is not 0. And similarly, B10 dual is B10. And finally, let's consider the example of standard Lie bialgebra structure on SL2, which we discussed yesterday as well. So we had the basis E, F, and H. So we have basis E, F, H of G. And so we have dual basis E star, F star, and H star of G star. And then the bracket is dual to the co-bracket, so it is a commutator of H star with E star is -1/2 of E star, commutator of H star with F star is -1/2 F star, and E star and F star commute, and delta is defined by these formulas here. So this shows that this G star is a Lie subalgebra in B plus B, and namely it's a subalgebra of elements. So there is a basis in the first copy of B, there is a basis x1 and y1, and here there is a basis of x2 and y2, and this is elements alpha x1 plus x2 plus beta 1 y1 and plus beta 2 y2. So and the co-product corresponds to the 1/4 here. All right, and then I give examples of duality of PoissonLie groups. So and of computing Poisson bivectors. So consider the two-dimensional case. So in the two-dimensional case, we have this non-commutative two-dimensional Lie group of upper triangular matrices, with upper triangular matrices with 1 in the lower right position, with real elements, and p greater than 0. So that's a simply connected group. And so let's say we take the Lie algebra and put on it the Lie bialgebra structure B0 beta. Then you can calculate by solving this differential equation or by using this homomorphism property that pi of PQ01 is beta times P inverse Q x wedge y. And for the algebra B10, it's given by this formula, 1 minus P inverse x wedge y. I think there must be a I think that maybe there is a mistake here because they're supposed to be equal to 0 at the yeah, it is okay. Yes, P inverse Q equals 0 when P equals 1 and Q equals 0, so it's okay. Right. Okay, so and then if G equals to SL2, you can compute this bivector most easily in the following way. So you first compute it for the upper triangular matrices 1, T, 0, 1, and then for the lower triangular matrices 1, 0, T, 1, and then for the matrix e to the t, 0, 0, e to the minus t, the diagonal, which is 0. And then you can obtain the rest by, well, any, so almost any element of SL2C, dense set of elements of SL2C, namely all the elements whose upper right left entry is not 0, can be written as a product of these three matrices in an appropriate order. So therefore, since we know how pi, what is pi of xy, we can compute from these formulas pi of any L. And it's an exercise to compute an explicit formula, what is pi of A, B, C, D. And we can also look at the dual group here. So the dual group is going to be, well, it corresponds to this Lie algebra that I described up here. So we should take pairs. So if you take complex entries, then this condition on this corner element is that it's not 0. So if I want a simply connected group, I should take universal cover, but I don't have to. And then you get these formulas for the Poisson bivector, from which you can, again, obtain by the product rule the formula for any element. So any questions up to this point? Okay, and so the next thing I want to talk about is co-boundary Lie bialgebra. So, so let G be a Lie bialgebra, and then so I will consider a special kind of Lie bialgebra structures. So a co-boundary structure on G so here I should say. So a co-boundary structure on G is an element R in wedge 2 of G, such that the delta equal to dr, which means so what does it mean? So this D is the cohomological differential. So this means the delta of A is A tensor 1 plus 1 tensor A commutator with R. And so, so if this delta is a co-bracket, which means it satisfies the Koji-Jacobi identity, and a Lie bialgebra equipped with a co-boundary structure is called co-boundary Lie bialgebra. And so if you have a Lie co-bracket already, so to be co-boundary means that this co-cycle delta is a co-boundary, which explains the terminology. And if that is the case, then this R is determined uniquely up to adding an invariant element of wedge 2 of G, because the invariant elements are exactly those for which this commutator here vanishes. So for example, when G is semi-simple, this space is 0, and therefore a co-boundary structure is completely determined by the co-bracket. There are many co-boundary structures on semi-simple Lie algebras, which we will discuss, but they are all completely determined by the co-bracket. So the question is now, what is the Lie bialgebra conditions in terms of this R. So suppose I don't give you a co-bracket. Suppose I only give you this R. And the question is, what condition on the R makes this co-bracket delta, which is dr, satisfy the Cauchy-Jacobi identity, which means define a Lie bialgebra structure. So for this purpose, I'm going to define this classical Yang-Baxter map, which is called CYB. And this is a map from G squared to G cubed. And it is given by the following formula. CYB of R is commutator of R12 with R13 plus R12 with R23 plus R13 plus R23. And so here, what do I mean by these things? So for example, R13 is, so if R is the summation of AI tensor with BI, then R13 is the summation of AI tensor 1 tensor BI. So this means that you should view these R, so this takes place in the enveloping algebra of G cubed, but actually ends up being in just G cubed. So this means that R13 means that I put the first component of R in the first position and the second component of R in the third position. So 1, 3. And similarly, R12 and R23. And now this expression also denoted by R bracket R. Because it really similar to the Schouten bracket, and we will show that it's actually closely related to the Schouten bracket. So a theorem of Greenfields says the following, that so if G is a Lie algebra and R is an arbitrary element in wedge 2 of G, then its co-boundary dr is a Lie bialgebra structure if and only if this classical Yang-Baxter expression of R is an invariant element in wedge 3. So it's easy to see that, in fact, if you apply the CYB to a skew-symmetric element lying in wedge 2 of G, then you get a skew-symmetric element lying in wedge 3 of G. But you don't always get an invariant element. And the condition for this to define a Lie bialgebra structure is that you get an invariant. This condition that is an invariant element is called the modified classical Yang-Baxter equation. Now, the proof of this is by direct calculation, but actually I will give a different proof using PoissonLie groups, which is much more transparent geometrically. That proof certainly, well, I mean, if you want to use Lie groups, this will only apply to finite dimensional Lie algebras, formally speaking. But actually, any Lie algebra, even infinite dimensional over complex numbers or real numbers, defines a formal group. And so you can just repeat the same proof for formal group, and that will be a valid proof for Lie algebra, any kind of Lie algebra, finite or infinite dimension. So I will explain this proof now, but before that, are there any questions?
I think not.
No.
I think you can go on, Pavel. I think there's no question.
Okay. All right. So so here is the proof. So suppose R is an arbitrary tensor, like I said, in wedge 2 of G. And suppose delta is the differential of R. So let's compute the corresponding bivector pi. So pi, so remember that we had this explicit formula. So this thing is little pi of e to the a. So then big pi of e to the a is obtained by spreading this by right translation. So I have to take this expression and multiply it by e to the a on the right. So this is, but this delta of a, well, dr means that it's adjoint a of r. And so I write it this way, but then this adjoint a cancels. Well, since we're working with formal series here, it makes sense. So this is defined by some power series. And I get e to the add a minus 1 r e to the a, which means e to the a r minus r e to the a. And so by analytic continuation, we can, or by using the cocycle condition, you can say that this actually holds for every x, not just for x of the form e to the a. So pi of x is xr minus rx. So this shows that the Poisson bivector of a Poisson-Lie group corresponding to a co-boundary Lie bialgebra is going to have a very simple form. We just take this r and we spread it by left translations and spread it by right translations, and then take the difference. And the Poisson bivector is just the difference of those two, left invariant bivector field corresponding to r and right invariant bivector field corresponding to r. So that formula is extremely convenient for calculation. So for example, well, r is so far arbitrary element, so we don't actually have a Lie bialgebra structure in general. So this pi of x is just a bivector field, and there is still a condition for it to satisfy, to define a Poisson bracket, a Lie bracket on functions. And that's the condition that the Schouten bracket of pi with itself, which is a trivector field, a section of wedge 3 of the tangent bundle, is 0. So let's compute the Schouten bracket. And so, well, first of all, if you compute the Schouten bracket of left invariant bivector with a right invariant bivector, that's automatically 0. Because if you compute, because the left invariant bivector is, by virtue of being left invariant, commutes with right invariant vector fields, which are vector fields corresponding to left translations. So therefore, when I commute this expression with itself, I only need to commute xr with xr and rx with rx, where by commute I mean Schouten bracket. But then, so we have to compute Schouten bracket of left invariant bivector field with itself. And then it turns out that that's exactly this Young-Baxter expression. So we again get a left invariant trivector field. And so this is an operation at the Lie algebra level. And that exactly turns out to be this Young-Baxter expression. So it's pretty easy to show. And what you get is xrr minus rrx. And this means that pi equals 0 if and only if this xrr equals to rrx, which exactly means that this rr is G invariant. Left translation of it is the same as right translation. So that completes this proof. So any questions up to this point?
Sorry, if pi bracket pi is 0, how do you deduce that r bracket r is 0?
So pi bracket pi is equal to x times rr minus rrx. And so if it's 0, this means xrr minus rrx is 0. And this means that rr is invariant with respect to adjoint action. So it's G invariant.
Yeah, thanks, I was confused. Thanks.
So, well, of course, I take the simply connected group. So, so G is the simply connected group. Okay.
Hi.
Yes.
So the reason why you need the simply connected Lie group is because this analytic continuation may not work if you don't take that one, right?
No. Well, I mean, the theorem that every Lie bialgebra structure, so Lie bialgebra structures on the Lie algebra G correspond to Poisson-Lie structures on the Lie group, is only true if this group is simply connected.
I understand, but in your proof that shows up because this analytic continuation will not.
No,
exist.
otherwise it's not important. It works, it still works. In fact, you can, so it, the elements of the form e to the a always cover at least a neighborhood of the identity. So,
right, but how does it go to the whole group? It will not go to the whole group, may not extend to the whole group. If it's not simply connected.
No, I mean, this is an equation. We are not extending a function. We're extending we have a function that satisfies some equation on some on a neighborhood of the identity, and it is analytic. So function vanishes. So the difference between left and right hand side vanishes on the neighborhood of the identity, and it is analytic. So this implies that it is zero everywhere.
But that expression that you wrote down for the bivector, it may not hold everywhere in the group.
No, it holds because we know that pi of x is, if pi of x exists, then it is an analytic function of x. And on the neighborhood of the identity, it is given by this formula.
Yeah, but okay, I see. Only in the neighborhood of the identity. Okay, good.
Yeah.
Thanks.
No, this formula makes sense. So if the formula makes sense everywhere and holds on neighborhood of the identity, then it holds everywhere.
Okay.
But actually also there is an even simpler way to check it, which is just check that this formula is stable under taking product. So if you take pi of xy, so let's say, so pi of xy is x pi of y plus pi of x times y. And so if you write x yr minus ry plus xr minus rxy, and this is, well, xry will cancel and you will just have xyr minus rxy. So if the formula holds for x and for y, then it holds for xy. But neighborhood of the identity generates the group. So if we know this equation on the neighborhood of the identity, we know it everywhere. Does it make sense?
Yeah, I think there's still some issues about compatibility, but that's fine. Okay, that's good.
Okay, so all right. So now in particular, there is an example. So if delta equals to dr. And r break, so in particular, it will be, this condition is satisfied with when bracket r is 0. In this case, we will get a Lie bialgebra. And this equation, r is 0, is called the classical Young-Baxter equation. Solutions are called the skew-symmetric classical R matrices, and the co-boundary Lie bialgebra is called triangular if this is satisfied. So let me now continue. So we have so this is a notion of triangular structure, and in fact, an important thing is that we can transport triangular structures along homomorphisms. So if you, this is something that we cannot do with general co-boundary structure. So if you have a homomorphism of Lie algebras from G to A, and R in wedge to G, a triangular structure, then if you take phi tensor phi of R in A, in which 2A is also a triangular structure. So this is something that doesn't work in general for arbitrary R such that R bracket R is G invariant, because if you have a G invariant element and you have a homomorphism phi from G to A, which is not surjective, we don't necessarily get an invariant element. So this type of structure is nice because we can transport it. So here is a classification of triangular structures. So co-boundary structures are difficult to classify, so we cannot do that in general, but triangular structures can be classified in terms of purely Lie theoretic terms. So suppose, so here is a proposition. Let R in wedge 2 of G be a solution of this classical Young-Baxter equation. Then XR and RX are Poisson structures on the corresponding group G, simply connected group G. Well, not Poisson-Lie structures. So they define left invariant and right invariant respectively. And the proof is we already proved it, because if you take XR bracket with XR, then this is the same as XRR, which is 0. And the same thing for RX and RX. So in general, we have XR minus RX, which is a Poisson-Lie structure, but XR and RX separately are not Poisson, even not Poisson brackets, because they don't satisfy the identity that Schouten bracket of this bivector with itself is 0. But in the case of triangular structures, which is this, these are both such structures. Here is a definition. A triangular structure R in wedge 2G is non-degenerate if it defines a non-degenerate map, invertible map from G to G star. Or you can say alternatively, it gives rise to a non-degenerate skew-symmetric bilinear form on G star. I'm sorry, I should write G star to G, G star to G. And this is equivalent to saying that the Poisson structures XR and RX on G are symplectic. So in this case, G has structures of symplectic manifold, left invariant and right invariant. And it, well, of course, it has to be even dimension. And so, so to classify, so we can reduce classification to the non-degenerate case. in the following way. So here is a proposition. And this proposition actually applies more generally, and we will need it more generally. So let R in G tensor G be a solution of the classical Yang-Baxter equation, which is R bracket R is 0. But we do not require that R is skew-symmetric. So it's more general than what we are doing. And we will need it in that more general thing. Then we can define two spaces, GR plus. It is the span of identity tensor F of R, where F is in G star. And GR minus, which is span of R tensor identity, of F tensor identity of R, where F is in G star. So in other words, we have two, so R defines two different maps from G star to G using, because it is in G tensor G, so we can replace, you can use the left copy of G or right copy of G to define that map, and GR plus and GR minus are images of them. And so we define these things, and then the statement of the proposition is that then G plus and GR minus are finite dimensional Lie subalgebras of G, and they're of the same dimension, which is a rank of this tensor. So here is a proof. So it's again easy to compute. So we give a proof for G star, for GR plus. So with GR minus is similar. So we take R equals to the sum. So let's call this number n, and this is going to be sum of I equals 1 to n AI tensor BI. So that's a representation of minimal length. So then this AI is a basis of GR plus, and BI is a basis of GR minus. And then the classical Yang-Baxter expression of R is what? Well, you have to R12 and R13 plus R12 and R23 plus R13, R23. So what is this R12, R13? Well, I claim that this is the sum over I and J, AI bracket with AJ, tensored with BI, tensored with BJ. And then the second thing is AI. So the commutation, there are two, here we have two ones, and that's why we have commutator in component 1. And here we have two 2's, so we have a commutator in component 2. So we have AI tensored with BI, AJ, BJ. And the third one is we have a commutator in component 3, so it's going to be AI, AJ, commutator of BI, BJ. And so, so what this implies that AI, so if this is 0, this means that the commutator of AI, so then we can compute, then let us apply BI star tensored with BJ star dual basis in components 2 and 3. And the first term will then get us AI, AJ, And then this is going to be a linear combination of AK, because the second and third term will just have one A. And that implies that GR plus is a Lie algebra. And also, another proposition is that GR plus and GR minus are also Lie coalgebras, Lie subcoalgebra. Of G. So this is in the case of R being skew symmetric, because delta cross 1 of R, which is the sum of delta of AI tensor with BI, is what? Well, this is so we have to commute first component with R plus second component with R. So that turns out to be R13 plus R23 commutator with R12. And by the classical Young-Baxter equation, this is the same as R13 commutator with R23. And so, so this is the sum of AI, AJ, tensor commutator of BI, BJ. And this shows that delta of GR plus is contained in GR plus tensor GR plus. Cool.
Pavel, sorry to interrupt. Maybe you can finish in 2 or 3 minutes, you think?
Yeah, definitely. So this is a Lie coalgebra, and so and the same as for minus. And the last proposition is the following: that R defines a non-degenerate triangular structure on G, if and only if. So we can take R inverse. If R is non-degenerate, we can take the inverse in wedge 2G star. So if you have a skew symmetric non-degenerate form, non-degenerate bilinear form on some vector space, you can take the inverse form on the dual space, which is just has a matrix in the dual basis, its inverse matrix to the original. And then this is a non-degenerate 2-cos cycle on G with values in the ground field K. So this means that eta of A, B, C plus eta of B, C, A plus eta of C, A, B equals 0. So I will explain the proof of this next time. But the benefit of this is that classical Young-Baxter equation is non-linear. It is quadratic. That's why it's hard to solve it and hard to classify solutions. But this is a linear equation. It's really an equation for a 2-cos cycle. So it really classifies central extensions of G. And so that's a purely Lie theoretic problem. And so we reduce the classification to purely Lie theoretic question. Okay, any questions?
Yeah, so there was a question on chat by Francis. Maybe Francis, you can just ask, I guess.
Hi, I was just wondering if the proposition right before, if you said that R had to be skew symmetric.
Yeah, it doesn't. No, so yeah, That's right. So the only thing it requires is that R, the symmetrization of R should be G invariant, because that's necessary for, so if you take commute delta of A is adjoint A of R, we need that to be skew symmetric. So it's a weaker condition, which is called quasi-triangular, and that's something I will explain at the beginning of next lecture. So you are right that it works a little bit more general. Other questions?
Yeah, you said that you could reduce the classification to the non-degenerate case. Can you say a few words about that?
Right. So we classify it in the non-degenerate case, and then, well, the previous proposition. So this in the skew symmetric case, I'll repeat that next time a little more detail. Skew symmetric cases GR plus and GR minus coincide because we have skew symmetric tensor, and so this is called support of this solution. And so this is a Lie subalgebra, and on this Lie subalgebra we have a non-degenerate solution. So that will imply that triangular matrices are classified by the following data. You need a Lie subalgebra in G and a non-degenerate two-cos cycle on this subalgebra. This subalgebra will necessarily have to be even dimensional in that case. Yeah. Other questions?
Okay, there's a question, so maybe let me get the microphone there.
Mm-hmm.
I should pick here. Yeah. So actually, it's more a general question on Poisson-Lie groups. So you take a map from G star to the Lie group G. G star the dual of the Lie algebra. Then it gives a bisection, and it's Lagrangian if its differential is symmetric for the duality pairing. I wonder if it interprets nicely in terms of Poisson-Lie group. Like, for instance, if we could find...
Yeah. So you emailed this question to me, right?
Yeah.
Yes, I will respond by email. I have to think about it.
Okay, thanks.
Mm-hmm.
Okay, sorry about that.
Other questions?